Hello everyone, it's my pleasure to introduce our work titled Class Conditional Sharpness Aware Minimization for Deep Long-Tailed Recognition. The authors come from University of Science and Technology of China, the Chinese University of Hong Kong, Tencent AI Lab, and the Zhejiang Lab. Our work mainly explores the varieties of deep long-tailed recognition models by providing some empirical and theoretical observations of current popular DLTR models. Start from these observations, we propose a class conditional perturbation operation to help each class seek flat minima. Our method research from a new angle in DLTR, that is parameter perturbation, which is orthogonal to the cousin DLTR regimes. Extensive evaluations demonstrate CCSM can achieve competitive performance. Our work targets solving a classical machine learning problem, that is long-tailed recognition, which exhibits a long-tailed distribution in its training set. And currently, there are various solutions to address this problem from different aspects. For example, there are some works focused on cost-sensitive rebalancing, augmentation-based rebalancing, and decoupling regime. But in fact, seldom works research on parameter perturbation. And in general optimization scenarios, a flat minima usually indicate better generalization. Thus, there are already many practical solutions to help seek a flat minima. And some of them have been applied to specific application fields, such as continual learning and imbalanced learning. Now a question naturally raises in our mind: are cousin DLTR models have flat minima? To verify it, we investigate the local minima status of mainstream DLTR models, such as ERM, LDM, MISLES, and GCL, by randomly perturbating the trained model 5 times and observe their loss values. From the right figure, we can observe that the loss function values of LDM and GCL fluctuate more than ERM. Therefore, we can conclude that LDM and GCL have sharper minima than ERM, which indicates a cast of DLTR models lack of flat minima. Now, another question is that can concentrate flattening operations help? Here we investigate for popular flattering operations and integrate them into aforementioned DLTR models. The results are present in the right figure. And it demonstrates that naive integration of general flattening operations with DLTR models can hardly bring improvements. Now let's look at the characteristic radius of flat minima. We derived a theorem from the perspective of Pack-Bayesian generalization bound. The first item of the derived upper bound can be approximated by the first-order Taylor expansion. Then we can obtain the optimal perturbation and its characteristic radius. Thus, we can derive the approximated optimal generalization bound. More details, please refer to our paper. And we should note that in long-tailed problem, the label marginal distribution is not identical between the training set and the test set, but it's reasonable to assume the conditional distribution holds. Hence, we can obtain the class conditional perturbation based on the previous derived result. And according to our theoretical and empirical observations, we can now introduce our method named CCSAM. We take decoupling as the basic framework and applying CCSAM in the first stage. In stage 1, we perturb the model parameters for each class in a mini batch, and finally optimize the perturbative loss. In the stage 2, we introduce the interlevel adversary sample generation mechanism to further train a response classifier. And it should be noted that CSAM can be integrated in most mainstream DLTR models. We evaluate CSAM on the mainstream benchmarks, and it achieves the state-of-art performance on CIFAR 10 LT and CIFAR 100 LT. It also shows competitive on large-scale datasets such as Places LT, ImageNet LT, and iNaturalist by generally augment the medium and the tail classes. Specifically, as a theoretical motivated average, CCSAM outperforms the naive application of SAM, which demonstrates the superiority of class conditional perturbation. And surprisingly, CCSAM even achieves the state-of-the-art performance under OLTR setting, which indicates it actually learns a response representation. We also conduct an ablation study to demonstrate the necessity of our derived perturbation, which includes both magnitude and direction. And both magnitude and direction contribute to the performance. And at last, we depict the loss landscape of each model here, from which we find the CCSAM as Fletcher minimal in both hand and tail classes. Thanks for your listening. If you are interested in our work, please feel free to contact me.